So let's consider a cubical satellite and in orbit around the sun. So this is our satellite, it's cubical. Something like this, and we have the sun here, and the orbit is going to be, well, circular, ideally, but yeah. And it's a distance at 2 AU. So we want to know the equilibrium temperature of the satellite, and we can solve this using an energy rate balance. So we look at how much, what the energy rate coming in to the satellites is, and we look at what the energy rate coming out of the satellite is, and then we can solve for the temperature. Now we know that there are two contributors to the energy rate coming in. So Q in, the dot represents the rate. So there are two contributors to this. One, there is energy coming from the sun, and yeah, that is going to be represented by the intensity times the area of absorption. So in our case, we have a cubical satellite, right? So only one phase will absorb the radiation coming from the sun, and the intensity, yeah, the intensity is going to be less the further away we go. And also, what we also have to account for is the absorption rate, because not all of the radiation coming from the sun will be absorbed, so we also have to account for that with the factor. Plus, there's another thing we have to account for, which is the heat coming from the electronics inside the satellite. So, well, that is given, so that Q is given, and it's an infrared radiation. And normally we would also have to account for an absorption rate. Now, but we know with infrared radiation, the absorption will be equal to, so the absorptivity will be equal to the emissivity, which is represented by the Greek letter epsilon. And now to the energy rate output. We know that the energy rate output is going to be, well, we have heat radiation coming out, and that is equal to, well, we have emissivity again, because it's emitting, right? Then we have the Stefan-Boltzmann constant. You shouldn't confuse that with the just normal Boltzmann constant. And times the temperature to the fourth times the area for the area that is emitting the radiation. So that is out. Now we can write out everything now. So we have intensity at 2 AU, which is, by the way, we know that the intensity is decreasing with 1 over r with the radius squared. So the intensity at 2 AU, we know the intensity at 1 AU, that is given. 1 AU is equal to 1,400 watts per meter squared. And with this given and this relation, we know that the intensity at 2 AU must be the intensity at 1 AU times 1/2, because it's 2 times bigger, 2 times further away, squared. So this is just this relation. So we can write this 1 AU. We can substitute this for the I. So that's going to be 1/4 times the absorption plus QIR epsilon. That's equal to the output, which is equal to epsilon Boltzmann constant T to the 4th, and the area of emission. Yeah, you already see we have T to the 4th, so we just have to solve this for T. So we will end up with the 4th root of, what do we have here? So I 1 AU to the 1/4 times 1/4 times A plus QIR epsilon divided by epsilon times Boltzmann constant times AE. So yeah, we basically have all the values given in this problem. Well, yeah. So we already have the intensity at 1 AU. That's 1,400. The absorptivity is equal to 0.8. So that is 80% of the radiation coming to hitting this surface is going to be absorbed. Then epsilon, so that's the emissivity, is 0.5. And yeah, the internal heat dissipation, that is this QIR, that is going to be 150 watts. And now what is remaining? Oh yeah, we need to know the area here. Well, the length of one of these sides is going to be 4 meters. And now we also have to think, I think I forgot this area here. Area of absorption. So the area of absorption is only going to be one side, so that's going to be 4 squared, which is going to be 16. So AA is going to be 16, and because it is emitting on all the sides, and we have a cube, so we have 6 sides. So we just have AE is going to be 6 times 16. And I already calculated this for you. Well, this is the temperature. So the temperature, if you plug in all the values here now. Oh yeah, the Stefan Boltzmann constant. This is something like 5.67 times 10 to the negative 8. Well, but this is usually always given. So yeah, you plug in basically all the numbers, and you will end up with 203 Kelvin, and that is it.